Thank you for stopping by our poster. My name is Kareem Aboayanah. I am a PhD candidate at the University of Toronto working under the supervision of Professor Giovanni Grasselli on the thermomechanical behavior of rocks. In this research, I am revisiting the thermal gradient cracking in granitic rocks and investigating the development of the thermal gradient fracture process zone. This fundamental research aims to provide deeper understanding of the cracking associated with the disturbance of the temperature field that is encountered in many underground applications. Uneven variation of the rock temperature induces thermal gradient stresses that can result in cracking if the rock strength is exceeded. Researchers have been using acoustic emission and computed tomography to investigate the evolution of thermal gradient cracking. However, these techniques are not suitable and challenging to track the fracture process zone and the crack opening in real time. In fact, these aspects of the fracture of the thermal gradient cracking are not fully understood, and this poster is the first attempt to address the evolution of the fracture process zone during thermal loading. In this research, we adopt digital image correlation, DIC, to track the fracture process zone and measure the crack opening displacement with the temperature variation. So why we are conducting this research? Disturbance of the in situ temperature exists widely in the lithosphere. It can be natural, such as magma migration and volcanic activity, or anthropogenic, such as in situ combustion, oil recovery, and thermal stimulation. For example, thermal gradient in the lithosphere can reinvigorate hydrothermal circulation through grain scale cracks, and it can explain plate tectonic convection through kilometric scale cracks. Also, thermal stimulation of rocks has been a viable method for hard rock breakage, which is widely applied and implemented in geotechnical engineering, enhanced oil recovery, geothermal energy exploitation, and tunnel excavation. In this image, magmatic heat source induces thermal gradient stress on the overlying layers that might result in thermal gradient cracking. So, how we are conducting this research? We use the 3D DIC system comprising 2 digital cameras, and we use the heating cartridge to heat the disk samples and to track the spatial propagation of the crack and the thermal gradient fracture process zone. 0.5 millimeter horizontal grid was used and the variation of the displacement along this grid line was observed, as you see here in this figure. The difference between the two ends of the displacement jumps at either side of the crack indicates the crack opening displacement. As shown here in this figure, the calculation of the crack opening displacement. Cracks also appear as strain localization zone on the major principal strain plot, and the width of this localization zone defines the width of the thermal gradient fracture process zone. A threshold crack opening displacement of 3 micron was adopted to locate the tip of the thermal gradient fracture process zone, while the critical crack opening displacement was used to define the end of the thermal gradient fracture process zone and the start of the traction-free crack. You can notice here an acceleration of the crack opening displacement after this critical crack opening displacement value. Here are some results of this research. As the heating cartridge was turned on, the center of the sample expands due to thermal expansion of the heating cartridge and the inner of the sample. And this expansion exerts tensile stresses on the relatively cooler far field and periphery of the sample. The tensile stresses are counterbalanced by the compressive stresses in the interior hotter part. When the tensile stresses exceeds the material strength, cracks nucleate, as you can see here on the major principal strain plots. With the temperature increase, these cracks extend toward the sample interior and through the coalescence of microcracks, and we have a macro crack propagated at this time step. Crack opening displacement in this figure exhibited different regime with the temperature evolution during the heating and cooling stage. First, it increased to 3.3 micron, which suggests a period of thermoelastic deformation, and this displacement represents the elastic crack opening displacement, which defines the onset of the thermal gradient fracture process zone formation after a period of thermoelastic deformation. With the temperature rise, crack opening displacement increased and reaches the critical value of 4.8 micron. The critical value defines, as we said earlier, defines the onset of the traction-free crack propagation, and the whole temperature represents the critical temperature for the thermal gradient cracking. This temperature at this time step represents the critical temperature. At this time step, crack opening rate sharply jumped, as you can notice at this moment. And after the micro cracks coalesced into the macro crack, we can observe a linear trend of crack opening displacement increase with the heating or the temperature, followed by a linear trend of closure during the cooling stage after the turning off of the heating cartridge. After this linear closure, the opening or the cracking opening displacement reached its residual value at the end of the experiment. In this figure, we show the length of the fracture process zone, which decreased with the increase of temperature and the propagation of the macro cracks until it reached the heating hole. And in this figure, we show that the width of the fracture process zone decreased from the sample periphery to the heating hole due to the increasing temperature in the inner part of the sample, and hence the increased micro cracking around the macro crack, which resulted in wider fracture process zone near the hole. Thank you so much.